Good evening, everybody. Now, uh, in my last class, I already completed the adjoint linear operator. Adjoint linear operator. Okay. So there are also some more things like least square approximation, least square approximation, and also there is minimal solution to a system of linear equations. Minimal solution to a system of linear equations. Minimal solution to a system of linear equations. So we already completed this thing, and due to the lack of some time, the least square approximation and minimal solution to a system of linear equations. I will not cover this thing, and I will provide you notes for these two chapters, and I will provide you notes in my description box. So in my YouTube, there will be a description box. So in the description box, I will provide you a link where you can download notes. Okay. So from that note, I will clearly understood, I think. So now today I will start what is normal linear operator. Okay. So now comes to normal linear operator. Okay. So before going to this normal linear operator, now we will associate lemma. So what is the statement of this lemma? Let T be a linear operator. Let T be a linear operator. Let T be a linear operator on a finite dimensional vector space V if T has an eigenvector. If T has an eigenvector, if T has an eigenvector, then so does T star. Then so does T star. Well proved. Okay. So what is the statement? Let T be a linear operator on a finite dimensional inner product. Finite dimensional inner product space, we can say. Let T be a linear operator on a finite dimensional inner product space V. If T has an eigenvector, then so does T star. That means if T has an eigenvector, then T star has also a eigenvector. Uh, we know these things. Suppose A is a matrix and uh, lambda is its eigenvalue, then we know these things. Ax equal to lambda x, and similarly Ax minus lambda x equal to 0. This implies Ax minus lambda Ax, this thing equal to 0. Then we can say A minus lambda Ax equal to 0. So when A is a matrix, and similar things also we can say for a linear operator T or for a transformation T. Same thing, in place of A, I can replace it by T. So this thing we already know for a matrix, and similar thing holds for a linear operator. So now comes to its proof. So given that T is a linear operator on a finite dimensional inner product space V, given that T is a linear operator, T is a linear operator on a finite dimensional inner product space V. Then T has an eigenvector. and we have to show that T star has also a eigenvector or also the same eigenvector. No, T star has also a eigenvector. So let V is a eigenvector of T. Suppose that V is a V is an eigenvector. V is an eigenvector of T. So what will happen if V is an eigenvector of T? Since V is an eigenvector, let V is an eigenvector of T with corresponding eigenvalue lambda. With corresponding eigenvalue lambda. With corresponding eigenvalue lambda. That means T is a operator. T is an operator, and it has an eigenvector V corresponding with this eigenvalue lambda. Okay, so if lambda is an eigenvalue and V is its corresponding eigenvector, similarly we will write this thing like if A is a matrix, then A is equal to lambda x, or A minus lambda Ax is equal to 0. So here same thing we also write for this linear operator, since lambda is an eigenvalue and V is its corresponding eigenvector. So we can write this thing T minus lambda I of V equal to 0, since lambda is its eigenvalue and V is its corresponding vector. So what we can write, then for any vector x belongs to V, what is the inner product of 0 comma x? Since one vector is 0, so inner product of 0 into any vector, this will be 0, and in place of 0 what we can write, this is T minus lambda I of V equal to 0. So in place of 0 I can write this is T minus lambda I of V. Okay, because lambda is the eigenvalue and V is the eigenvector and of T, that's why this thing holds. So in place of 0 I can put this thing. Okay, inner product of T minus lambda I of V with x is equal to 0, or in place of 0 I can put this thing. So then what I will do in the next step, whatever is here in the first vector, I can take it into the second vector by taking it star. So we can write this is V, and this thing we can take to the second component and the second vector, that is your T minus lambda I star. We know already from the last class, if something will change its position from first to second or second to first, then there will be a star. So this will be T minus lambda I star of x. Then we can write this thing as this is V, and what is T minus lambda I star? T minus lambda I star is your T star minus lambda bar I. T star minus lambda bar I of x. T minus lambda I star, this is actually your T star minus lambda I star. So what is T star? T star is T star remains unchanged, and lambda is a scalar. That scalar may be a real scalar or a complex scalar. This thing depends upon its field. So if lambda is real, then lambda star will be lambda. If lambda is complex number, then lambda star will be lambda bar. Then what is your I is the identity matrix, then I star, star means the conjugate transpose. Okay, in the last class we already discussed. So T minus lambda I whole star is equal to T star minus lambda bar I, because I star is I. Okay, and lambda is a constant, so only its conjugation is here. Okay, so T minus lambda I star can be written as this is T star minus lambda bar I. then x. So what will be this thing now? So 0 is equal to inner product of this thing. And also we know this thing. Two vector x1 and x2 are said to be orthogonal. In the last class also we said something about orthogonal. So x1 and x2 are said to be orthogonal, or any two vectors are said to be orthogonal if and only if their inner product is equal to 0. That means inner product of x1 with x2 is equal to 0. So if this thing holds, then x1 and x2 are said to be orthogonal. If x1 and x2 are said to be orthogonal, then their inner product is 0. This is if and only. Okay. So if inner product of these two things is equal to 0, we will say that both these things are orthogonal to each other. So we can write hence V is orthogonal, hence V is orthogonal to T star minus lambda I, is orthogonal to T star minus lambda bar I x. And you know T star is a linear operator. Linear operator means just a function. So T star minus lambda I, you made it this thing as a function. So T star V is orthogonal to this thing. That means V is orthogonal. That means V is orthogonal to the range of T star minus lambda bar I. Okay, you know, if f is a function from a to b, suppose this is a, this is b, and if this is x, then this is your f of x. So f of x means this is the f of x. This is the range of f. So a similar thing. Similarly, we can say this is the v is orthogonal to the range of t star minus lambda bar I. So since V is orthogonal to the range of this thing, so what we can say next? So we can say T star minus lambda bar I is not onto. That means T star minus lambda bar I is not onto. Okay. So since T is a mapping from T is a linear operator on V, so T star is also from V to V, and whatever the T star minus lambda bar I, this thing is also from V to V. This is T star minus lambda bar I. So this thing is also from uh, also from V to V. Since V is orthogonal to this range of this one, and so T star minus lambda bar I is not onto. So there is a concept from uh, S for, you know, S, and what is S for, and both these sets are suppose S is a subset of V, and S for means the, so we already know this thing. Suppose S is any subset of a vector space V or an inner product space V, then what is your S for? S for contains those Y such that Y is perpendicular to S, or those, it contains those Y such that inner product of xy equal to 0 for all x belongs to S. Okay, concept is same. S bar means it contains those vectors which are perpendicular to S. Okay, And you may also note that S union S bar is equal to the whole this vector space V, and their intersection is only the zero vector or the identity vector. So if V is orthogonal to this one, that means this V is lying in the fork of this one, in the fork of this one. So since V is belongs to the fork of T star minus lambda bar I, that means V does not belongs to T star minus lambda bar I. Okay, since V is orthonormal to the range of this one, that's why I can say V belongs to fork of this thing. Since V belongs to fork of this thing, that means V is not lying in T star minus lambda bar I, because uh, any set and on its intersection, sorry, on its fork, the intersection is only the identity element. Okay, and we are taking here V is the eigenvector, and V eigenvector means this is a it is always non-zero. Okay, so T star minus lambda bar I is not onto, that means V is not lying on this T star minus lambda I, and we know that T star minus lambda bar I, this is a map from V to V, and since there exists an vector V belongs to capital V such that its image does not exist here. Okay, the image is not here. That's why this is not onto, because this thing does not belongs to this one. So since this is not onto, so what we can say, this is not onto. Also, you may think that a range of T star minus lambda bar I is not your whole V. Okay, since V does not belongs to this thing, so a range of this one is not equal to V, so this is not onto, then we can say hence it is not 1 1. T star minus lambda bar I is not 1 1. This thing also, you know, since V is a finite dimensional inner product space, and T from V to V is 1 1 if and only if T is onto. So if T is 1 1, then it is onto, or if it is onto, then it is 1 1. If V is a finite dimensional inner product space. So since this thing is not onto, so we can say this thing is not 1 1. Thus, what we can say, so since this thing is not 1 1, so we have also another concept, since this thing is not 1 1, uh, if T is not 1 1, if T is not 1 1, then null space of T is not equal to the 0 vector. Or you already know it, if T is 1 1, then null space of T contains only 0 vector. Similarly, here you can say if this thing is not 1 1, so null space of T star minus lambda bar I contains non-zero vectors. Okay, this thing contains non-zero vectors, and that non-zero vectors acts as the eigenvector of T star. Okay, so whatever the non-zero vector you will find here, that will act as the eigenvector of T star. Corresponding to this eigenvalue, corresponding to this eigenvalue lambda bar, because t has eigenvalue lambda, that's why you are saying that t x or t v equal to lambda v. Lambda is its eigenvalue and v is its eigenvector. That's why t v equal to lambda v, and I am saying that whatever the t star, it has also an eigenvector. So the eigenvector will be that v, and it has the corresponding eigenvalue lambda bar. Sorry. It has the corresponding eigenvalue lambda bar, and that vector is same that v. So here we just prove that t has an eigenvector. So if t has an eigenvector, then t star has also eigenvector. And what is that eigenvector? That will be that v. Here we have not proved that thing. Here we just prove that since the null space of this thing contains non-zero vector, and that non-zero vector will act as the eigenvector of t. And this is the extra case that this t star has this corresponding eigenvalue lambda bar, and this whatever the t star, that has also the same eigenvector v, and this thing will prove later, okay, also in today's class. So now comes to another note. A polynomial is said to be split. A polynomial is said to be split. This thing you already know this word from your group theory or from ring theory. A polynomial or said is said to split if it factors into if it factors into linear polynomial. Okay, a polynomial is said to split if it factors into linear polynomial. Like example, suppose if I will say x square minus 4. So if I will split this thing as x plus 2 whole into x minus 2. Suppose my field will be R, then this thing is split into this thing, and all these things are linear in R. So I can say this polynomial is split as this thing, as we can write this thing as a factor of linear polynomial. Similarly, if I will write x square plus 2x plus 1, I can write this thing as x plus 1 whole into x plus 1. So this thing also splits, this thing also splits. So if somebody will write x square minus 2, so this thing cannot be splitted in R, because if somebody will write this thing as x plus root 2 whole into x minus root 2, so whatever the things I have written, this plus root 2 minus root 2, this thing doesn't belongs to R. Here this plus root 2 or minus root 2, this thing doesn't belongs to R. That's why we can say this thing does not splits in R. Does not splits. Does not splits in R, because this thing cannot be written as a product of linear factor. Okay, these things are a linear factor not in R, but these things are these things are linear factor in R. Plus root 2 and minus root 2 belongs to R. Belongs to R. So this thing splits. Sorry. Splits in R. But if I will take x square minus 1, so this thing can be written as x square plus 1. Okay, x square minus 1. This is your x. whole into x minus I, which is x square minus I square, x square minus I square. So this is x square plus 1. Okay. So x square plus 1, this thing can be written as your x plus I whole into x minus I, and here these things are this plus I minus I. This thing does not belongs to R. So uh, this x square plus 1 of this polynomial does not splits in R. Does not splits in R. Okay, because this thing, if somebody will say this thing can be written as a linear factor, but this thing can't be written as a linear factor in R, because whatever the I and minus I are written, this thing doesn't belongs to R. But this thing, everybody will say this thing splits in C. This thing splits in C, because this I and minus I belongs to C. Okay, so this is the meaning of split. If any polynomial can be written as a linear factor, then that is that then you can use this thing split. Okay, now we'll just come to a statement of score theorem. I will not prove it, only the statement I will give to you. Let T be a linear operator. Let T be a linear operator. T be a linear operator on a finite dimensional inner product space V. Suppose that the characteristic polynomial of T splits. Suppose that the characteristic polynomial of T splits. And you know what is the characteristic polynomial? If okay, I will go to later. Suppose that the characteristic polynomial of T splits, then there exists an orthonormal basis. There exists an orthonormal. There exists an orthonormal basis beta for V such that the matrix TB is upper triangular. Such that the matrix TB such that the matrix TB is upper triangular. So what is the Square's theorem? Let T be a linear operator on a finite dimensional vector space V. T is a linear operator on a finite dimensional inner product space V. That means T is a mapping from V to V, and V is a finite dimensional inner product space. Suppose that the characteristic polynomial of T splits. So what is the characteristic polynomial of T? Uh, since T is a operator, and you can find the characteristic polynomial of T, because from T, suppose lambda is an eigenvalue, then what is the T minus lambda I? T minus lambda I into x. If this or T minus lambda I, simply T minus lambda I of x, this will give the characteristic polynomial of T. So whatever the characteristic polynomial of T you will get, if this thing splits, then there exists an orthonormal basis beta. So if the characteristic polynomial of T splits, then there exists an orthonormal basis beta for V such that the matrix TB is upper triangular. Matrix TB means we already discussed what is TB. TB is the matrix associated with this linear operator T corresponding to this orthonormal basis beta. The matrix T is the matrix associated with the trans or with the linear operator T, corresponding to this orthonormal basis, to this basis beta. This is the TB, and this TB is upper triangular. You know what is upper triangular? Upper triangular matrix. This is a matrix uh, whose lower diagonal elements are 0. Suppose what I can say. Suppose this is a 3 cross 3 matrix, and these are the diagonal elements. Sorry, what are the main diagonal elements? These are the diagonal elements. So this is your main diagonal, and upper triangular means the lower diagonal elements are 0. That means these things are 0. So whatever may be these things may be 0 or non-zero. Okay, but the lower these elements, what are the elements present below the main diagonal? This is the main diagonal. So whatever the elements present below the main diagonal, these things are 0. Then this will be a upper triangular matrix. That means in a 3 cross 3 matrix, these 3 elements are 0. What are below this diagonal main diagonal elements? Okay, so whatever the matrix TB you will get, that is a upper triangular matrix. So I will not go to prove it, but you will use these things. So we just understood what is the statement is saying. So now we will come to what is the definition of normal. So what is normal or normal linear operator? Okay. Let V be an inner product space. Let V be an inner product space. Let T be a linear operator on V. Let T be a linear operator. T be a linear operator on V. Then T is said to be normal. Then T is said to be normal if T star equal to T star T. Okay, so suppose V is a 5 inner product space and T is a linear operator on V, then that linear operator T is said to be normal if it satisfies this condition. T star equal to T star T. That means the product of T star, if it is commutative, then it is said to be normal. T is said to be normal. So in matrix space also you know this thing, an n plus n matrix, an n plus n a real or complex matrix, an n plus n real or complex matrix A is said to be normal, if A star is equal to A star A. And you know what is the meaning of A star in a matrix? A star means this is the conjugate transpose of A. Conjugate transpose of A. Conjugate transpose of A. There is a conjugate and this is the transpose. So A star means this is the conjugate transpose of A. So this is the definition of normal for a linear operator and for a matrix, whether it is real or complex. And then make another note here. T is normal, a linear operator. This type of linear operator. T is normal if and only if the matrix T, if and only if the matrix TB. What is the matrix TB meaning? Means this is the matrix associated with this linear operator T corresponding or with respect to this basis beta. So a linear operator T is normal if and only the matrix associated with this transformation T or with this operator T with respect to this basis beta is normal. And when we will call this matrix normal, here we already discussed a matrix A. That means a linear